Example number 2. We're going to deal with ellipse. We want to find the area of a generic ellipse whose center is at the origin. Now some of you go, a what? Ellipse. Remember conic sections. Find the area of the ellipse x squared over a squared plus y squared over b squared equals 1. Just look at this example, this expression here, and you recognize that the ellipse or the circle is a special case of the ellipse, if you don't remember it from conic section in pre-calculus. If, for instance, A and B are equal to each other, let's say they equal R, then you end up having x squared over r squared plus y squared over r squared equals 1. You rearrange it and get x squared plus y squared equals r squared, which is the circle. So really the circle is a special case of the ellipse. The ellipse itself, if I'm sketching it, this ellipse is centered at the origin, and the values of x and y represent horizontal and vertical vertices, respectively. For instance, if this is the ellipse, this point will be A and 0, this point will be negative A and 0, this point on top will be 0 and B, and the vertex at the bottom will be 0, negative B. Now I'm looking at this, and I need to find the area. Obviously, I need to integrate something here to find the area below the curve. But I consider the symmetry. We have both symmetry about the x-axis and the y-axis. So instead of calculating the whole damn thing, I can calculate only 1/4. Okay? And in this quarter, both x and y are positive. Okay? So it's convenient. Furthermore, the boundaries of x are 0 to a. So I know two things, that y will be positive here and x will go from 0 to a. And if I can rewrite, this is not a function. Obviously it's not a function because it failed the vertical line test. So is the circle. But if I can solve for y, then I'll have a y squared equals something else, and y equals the square root, plus minus square root. So I'll take only the plus, okay, and I can write only 1/4 of the curve. This and this, just this quarter, will be y equal f of x, where x is positive and y is positive, like so. Okay, again, just the quarter. So we're going to solve for y first, and this is the equation. So I'm going to say that y squared over b squared equals 1 minus x squared over a squared. I can write it as common denominator will give me a squared minus x squared over a squared, right? Y squared will be b squared. I'll multiply everything by b, so I can factor out the, I can just pull out a squared, and then I have a squared minus x squared, and finally y equal plus or minus b over a square root of a squared minus x squared, which we just learned how to deal with this type of expression. So again, we restrict, okay, restrict the curve x squared over a squared plus y squared over b squared equals 1 to the first quadrant where x is positive or equals 0 and y is positive equals 0, right? Then we have the integral, or we can say that y equals positive b over a square root of a squared minus x squared, and x goes from 0 to a. So now I know that I'll have 1/4 of the area if I'll integrate this thing. Okay? So the area the area will be 4 times the integral from 0 to a of this curve. D over a times the square root of a squared minus x squared dx. Okay? 4 times the area under the area of the first quadrant. Okay, so this is my integral right now. And of course I can pull out b over a, so I'll end up having 4b over a, the integral from 0 to a of the square root of a squared minus x squared dx. Substitution, this is the sign substitution if you remember, right? So we're going to substitute x equals a sine theta, and of course dx, let's not forget, will be a cosine theta d theta. And now the integral looks like 4. Wait a second, before we go there. What do I need to do at this point? Because I'm substituting, now I'm operating with the variable theta, I need to adjust the boundaries. Okay? And because this time it's a definite integral. What we did in the first example was indefinite integral. We didn't care about the boundaries, but now we need to adjust boundaries. So, let's see if this is dry enough. So let's say adjust the boundaries. Let's say we have, when x equals 0, it means that a sine theta equals 0. And remember what we talked about, our interval, our domain, on negative pi over 2 to positive pi over 2. The only time where theta equal, when the sine equals 0 is when theta equals 0. And we don't have to worry about theta equals pi or theta equals 2 pi because pi and 2 pi are not in the domain of the invertible function. So that's why we restrict the domain. Now what about when x equals a? Well, when x equals a sine theta equals a, it forces sine theta to equals 1 or theta to equals pi over 2. So now we can adjust the boundaries, and we're going to say that a equals 4b over a, the integral from 0 to pi over 2, like so, and instead of the radical, we have, where is it? We already done this, right? Remember, this is a squared minus a squared sine theta, or we have a squared. Let's do it. It will be a times the square root of 1 minus sine squared theta, the same thing we had in the previous example. D theta, dx is a cosine theta d theta. So we have a squared, so we end up having 4ab, a squared over a, the integral 0 to pi over 2 of cosine theta squared d theta. Okay, this gives you cosine theta, and you have another cosine theta. And remember the half angle or the double angle? You do? Did I do something wrong? I have a times a divided by a. Okay. Any other question? Are we good here? Lead me. Are we on this side? Left side? Yeah. Area of, I have two ofs of the first quadrant. This is erased. Thank you. Yeah, it's 4 times the area of the first quadrant. Going back to the previous image, okay? Instead of calculating the whole ellipse, we calculate the shaded area multiplied by 4 because of symmetry. All right. Now, what do we have here? We're going to substitute. So we have 4ab, the integral from 0 to pi over 2. And remember the double angle identity, right? 1 plus cosine 2 theta d theta. Okay, so we have a b divided by 2. And we can break it down into two. Well, actually, we can find out the antiderivative right there. The antiderivative of 1 is theta, and the antiderivative of cosine 2 theta is 1/2 sine 2 theta. So it's 1/2 sine 2 theta. Andy, go ahead. It's 4ab divided by 2. Yeah, it's 2ab. Thank you. So we have 2ab. And now, here's the thing with the sine 2 theta. Whether it's theta equals 0 or pi over 2, 2 theta will be pi or 0. The sign will be 0. So we can ignore the second term, the second expression. All we have to deal with theta, and of course this will be pi over 2, right? Minus 0 if you want, or we end up having a b pi. How can we verify this to be the correct solution? Go back to the comment I made early at the beginning of the example. What did I say about the ellipse? Manny, you want to respond to that? Okay, before you ask a question, let me see if somebody is willing to answer my question. How can we verify that this is the correct answer? Well, to answer a question is recall what I said at the beginning. Do you want to say? Exactly. All right, you are very correct. If you look at, if the ellipse is a circle, then A equals B equals R, and here we have pi r squared, which we know to be the area of the circle. So you know that this is the right answer. Manny, your question.